So I think before I begin, I should make a qualification. I've been to a few of these events, and a lot of them seem to be about prediction and how we can improve prediction performance. This presentation is going to be slightly different. So social scientists, or economists in particular, we're interested in two things. Usually we're interested in prediction, but often we're also interested in measuring the marginal impact of a particular variable varying, especially if it's varying exogenously. And in this presentation, I'll be focusing on the latter. So while this model can be used and is used to improve prediction, I'm going to be using it to try and get more precise estimates of a particular variable that I'm interested in. And that is, how much extra in rents do you pay if you live next to a train station? So one other thing that I'd like to mention, this talk is more about kind of my evolution of thought, how I've come across this model. So I started with a particular question, I was trying to solve it. The existing tools didn't necessarily meet my needs, did some research, stumbled across this framework, and then went on with it, saw where it led. So hopefully through the talk I can kind of show you how my thought has evolved. So yeah, like I said, I moved to Sydney about a year ago for work, and I moved up from Melbourne, and I was just kind of surprised how much more expensive rent is in Sydney. So I started measuring essentially how much extra am I paying to have a car spot in my unit, how much extra am I paying to live next to a train station, just trying to determine, for example, whether it's even worth having a car, given I drive it once a week. And one thing in particular that I was interested in is this kind of rental premium to live next to a train station. So I'm a person that struggles to wake up, so living close to a train station is very important so I can get to work on time. And essentially I just want to know how much extra I'm paying to live close to a train station, which I am. And that's in a particular area, but I just wanted to kind of know how it varies by area, not just the area I live in. So essentially that's what I went about to do. So the first challenge was data. That was solved. I'll discuss that once I get to the data section. But the second challenge is modeling. So from my economics training, there's kind of four approaches that came to mind. So, the four ways which I could go about this. I could simply run a separate regression on the data for the areas of interest and just look at the coefficient or the parameter, the coefficient on the time it takes to walk to a train station. Alternatively, I could pool all the data as if they're independent from each other and just look at the coefficient on, again, that variable of interest. The third approach is to pool all data but have dummy variables for each area. So understanding that prices are probably going to be correlated within geographies or within areas. And then the fourth method essentially just amounts to pooling all the data but have a dummy variable for each area and interact that dummy variable with the train station proximity variable. Now the fourth approach is actually quite similar to the first approach. But the only difference is these other covariates that I'm including, interacting them with the area dummy, so there's kind of less parameters to estimate. But in essence, model 1 and 4 will create similar problems. So now the problem, so one thing that kind of crossed my mind is that, it is very much possible that in different areas, people attach different value to live next to a train station. So it just could be that in the inner west, lots of people work in the city, so they want to get to work on time, so they value living next to a train station. The northeast, lots of people, say potentially tradies, I'm not sure, they jump in their car and they go to a site of work, so there's no real value associated with living next to a train station. So models 2 and 3, given that they'll average the impact of living next to a train station, it's not really useful to understand how living next to a train station varies. The value of living next to a train station varies by area, simply because you're averaging the impact of living next to a train station across all areas. So any method that pulls the data just kind of wasn't going to get me to where I wanted to get to. Now model 1 and 4 does get me to where I want, in that I can observe the variation by area, but then I was confronted with data challenges. So different postcodes, so I'm looking at postcodes, I'll address that later, have variation in their sample sizes, and therefore it makes it difficult to kind of get reliable statistical inferences on the parameter of interest. So, I said some areas, you're left with between 300 and 400 observations. You may say that's okay, but then the question is, given the way I'm constructing the sample, which I'll talk about, how many properties are we going to get next to that are close to train stations relative to properties that are far from train station to get the necessary variation to tease out the impact of living next to a train station. So there was kind of, there was two problems. One was essentially the The pooling models were averaging the effect. I couldn't get the variation within areas that I was interested in, because again, I want to make a decision of where to live given the cost of these different factors. And the other models which kind of have these separate parameters for the variable of interest, you just have insufficient observations and you get imprecise estimates. So they were kind of the challenges that I was confronted with. Now, if for all the postcodes I had large samples, then I could just go with either model 1 or 4 and it'll be end of story. You know, if the samples were sufficiently large such that I could get reliable estimates on the parameters, then really I wouldn't even need to look into hierarchical modeling. I could just have separate regressions. But when you're dealing with data, you often don't get it in the way that you want, or the sample size is not sufficiently large, so you've got to kind of find the compromise. Now, what I say here, so these two approaches seem to be end of two extremes. And you should notice that there's like a tension literally. So you either have a situation where you have high bias, low variance. So that's when you pool the data. You can imagine that the estimates are going to be highly biased, although they're going to have low variance. And the other extreme is that you have essentially low bias but high variance. So when you model each area individually, you're going to minimize the bias, but those estimates are going to become imprecise. So when you deal with these two models, you've got this tension. And the hierarchical modeling is essentially a solution to this kind of tension. Okay, so the key thing is with hierarchical modeling is that with many statistical applications, they involve multiple parameters, which we can assume that they come from a similar distribution, also from a master distribution. So you can think about living next to a train station. Right? While the value is going to vary by area, we can safely assume, I believe, that those coefficients or those estimates come from a similar master distribution. It's not just the kind of the value of living next to a train station, but just the mean price itself. Right? So while the mean price is going to vary from postcode to postcode, it's safe to assume that they probably come from a similar distribution. And that distribution will probably represent Sydney quite well. And here, this is essentially the example that I give. So while the value living next to a train station, let's call it beta, should vary across areas, it's reasonable to expect that the estimates of these values, the beta j's, should be related to each other. Now this is the kind of key thing. So by modeling the different areas within my data, by using dummy variables or running separate models, you're essentially assuming, you're implicitly assuming that nothing can be learned from the other areas. Okay, so you can imagine if you live in Marrickville, right, and you estimate a parameter for Marrickville, if you do a separate model, you're saying that nothing can be learned about the Marrickville parameter by looking at the Stanmore or Elwood, Earlwood estimates. That's what the separate model's doing. It's essentially throwing away information. And when you're trying to get a precise estimate of a parameter, you should use all information that you can to minimize the imprecision. And that's what models 1 and 4 were doing. They're essentially throwing away information. So, and again, with hierarchical models, especially a Bayesian hierarchical model, when we have such a relationship where the parameters kind of for the different areas come from a master distribution, okay, they can be modeled quite neatly by assuming that the prior distribution, so in this case the prior distribution of the beta j's, are viewed as a sample from a common population distribution. So you can immediately see that this kind of problem fits quite nicely with a Bayesian framework. And I'll be quite honest, so with my training at university, it's from a, I have a frequentist training, and I didn't really appreciate Bayesian statistics in the little bit of training that I received during my first year. But when it came to solving this problem, I really started to appreciate the power of Bayesian statistics, especially in this kind of hierarchical modeling. So the hierarchy arises in this kind of model because the model parameters, because the model for the parameters sits above the model of the data. And I'll show a diagram in the next slide which will make that clear. But the kind of key thing to keep in mind, by using a hierarchical model, you're essentially sharing statistical strength across the different areas. And that's the kind of key part. So it's, so this is kind of view held by others, but if you have a data which has a hierarchical structure, your default position should be hierarchical modeling. Because like I said, whenever you're trying to estimate a parameter and minimize the uncertainty surrounding that parameter, you should use all information available to reduce the imprecision. And a hierarchical model does that. Okay, so this is just the structure of a hierarchical model. Not sure if the laser, yep. So here we have essentially the observations for the different areas. So again, we can think of this as the rental properties across the different postcodes. And you're trying to estimate parameters for each area. So this is the parameter of living close to a train station, say in Marrickville, close to living to a train station in Chatswood, and so on. Now with a hierarchical model, what you're doing is you're saying these parameters here come from a common population distribution. And in trying to fit this parameter here for this area, it's going to inform this distribution here, and that in turn is going to inform this parameter here. And likewise, this parameter is going to inform the distribution here, and it's going to affect the parameter here. And this is how the statistical information is shared across the different areas. So it allows you to get area-specific coefficients while essentially maximally using the information maximally. So the other benefit of hierarchical models is that essentially if you pull the data and you have samples which are overrepresented, those samples, so areas which are overrepresented, those areas are going to dominate the coefficient. Hierarchical models have this other benefit that they essentially prevent oversample groups from impacting or dominating the inference. And that's another key benefit of using hierarchical models. So moving on. So this is the model that I use to estimate the impact of living next to a train station. So, sorry, it's just the acute angle. So what we have here is the rental value. So this is the weekly rental value in log units for property I in property J. And I'm saying that that is a function of just the mean in postcode J. And it's also linearly related to the time it takes to walk to the nearest train station, the WIJ. So that's the time it takes to walk from property I in postcode J to its nearest train station. And what I'm interested in is this beta J for all these different postcodes. So I have all these other covariates, but they're not really of interest. All they are is trying to, they're just acting as controls to make sure I don't have any confounding variables. So for example, if all the properties next to a train station are small, have less bedrooms or units, and you don't include those covariates, then essentially what you're going to find is that living close to a train station, actually you pay less for it in rent. So it's important to control for these covariates, and that's all that they're doing. And here essentially they're just property specific covariates, which is the number of bedrooms, bathrooms, whether it's a unit, and whether the unit has a car space. And then we just have this idiosyncratic error component, which is normally distributed of mean 0 and standard deviation sigma j. So just kind of a few things here. So why am I converting the rental values to log units and the time it takes to walk to a train station to log units? Well, there's three reasons why I do that. The primary reason is because I believe that there's the marginal impact of living next to a train station. So my prior view is that the marginal impact of living next to a train station should decline as the time to walk to nearest train station increases. So what do I mean by that? Essentially, whether you live 50 or 60 minutes away, the value should be very, very small. But if you live 10 to 20 minutes away, the value should be very large. So essentially having the time to walk to nearest train station log units and the rental value in log units just kind of captures that non-linear relationship. The other thing is, this becomes an elasticity. So we know for a 100% increase in the time it takes to walk to a train station, we get the percentage change in the rental value. The other key benefit to having things in log units, it just makes specifying these hyperparameters, the prior distributions of these hyperparameters, it makes specifying them easier. Because these are elasticities, they shouldn't be too different across the different postcodes. Okay. So moving on. So this is essentially modeling the hierarchy of the data. And these are the actual parameter estimates, the values for the prior distribution that I use. So here what you have is essentially the mean of the different postcodes, so the alpha 1, alpha 2, up to alpha n. And then I say that they all come from a common population distribution, which is normally distributed with mean mu alpha and standard deviation sigma alpha. And in turn, this distribution has its own prior distribution. And for these prior distributions, I essentially try to have a flat prior such that the data informs as much as possible what this mu alpha and sigma alpha is. Okay, so this is where the hierarchy comes in. So you've got the postcode level parameters. They come from a common population distribution. And in turn, we're trying to learn what the parameters is for this common population distribution. And we specify a prior for these parameters in turn. And as you can see, these are quite flat priors because I want the data to drive the estimates for these values. And similarly, I have a very similar structure for the value of living next to a train station. It's normally distributed with mu beta and sigma beta, and these in turn have a flat prior as well. So the data is going to essentially help us learn what these parameters are. Okay, so and these are just the prior distributions for the other parameters. Kind of nothing out of ordinary, it's just essentially informed by the work I've been to date with this data and just seeing how property prices, rental value prices vary by as the number of bedrooms increase, the number of bathrooms increase, whether it's a unit and whether it's a car park with a unit. Okay, so I think there's nothing special about these priors, but they have to be in there. Okay, so now to the data. So how did I construct the data? So initially I said that the first challenge was data. So I wanted to test a particular hypothesis. I needed to get my hands on the data. So what I use, where's the laser gone? So I have roughly 62,000 rental advertisements across 100 postcodes in Sydney. This data is from the months of January to November of 2016. Just kind of a little bit of background how I obtained this data. So this is nothing to do with, like, wasn't done during my work, it was just done during my private time. These rental advertisements essentially come from a popular rental website online, which I just scraped at the end of each month. So that's where the data source is. So won't specify which website it came from, but I just got them from online. So when it came to kind of cleaning the data was quite messy. So, you know, people advertise car parks, people advertise share rooms. So all these I had to get rid of. Some real estate agents display prices in monthly prices as opposed to weekly. So I had to deal with that. And so apart from dealing with that, which was relatively straightforward, essentially any extreme values I just removed from the sample. So, and by extreme I mean mean absolute deviations away from the median. I just deemed them to be either a car park or somebody put by accident the monthly price as opposed to a weekly. I also removed postcodes that are close to the CBD. So what's the motivation for that? Well, my idea is that you value living next to a train station because you want to catch it to get to work. If you live within the CBD or very close to it, you can just walk or ride your bike. I don't know, whatever people do. So I just assumed that the impact in these areas would be zero. So I removed that. I also removed all postcodes that are very, very far from a train station. So the whole of southeast Sydney, there's no train station there. The whole Mossman area, there's no train stations there. So again, I got rid of those suburbs because there should be no impact of living next to a train station because they're just very far from a train station. So how did I calculate the nearest train station? So the first thing was to determine the locations of the train stations. And I did that using OpenStreetMaps database. So you can use the Overpass API. You can specify a bounding box and request the coordinates for all train stations. So using OpenStreetMaps, I got the coordinates of all the train stations. Now to work out the time it takes to walk to the nearest train station, that was a two-step approach. So the first step was to determine the geolocation of the property. And you can in Sydney, there's actually the New South Wales government provides a free facility to get a geocode of the property, but you can use Google Maps or you can use Bing Maps. They can all have geocoding services. And then the second step was to essentially determine how long it takes to walk to the train station. And to do that, I determined the 3 nearest train stations as a crow flies using the Haversine formula. And then I used Bing Maps to determine how long it takes to walk to each of those train stations and selected the minimum. So that in turn gives us the kind of the time it takes to walk to the nearest train station. So this is a map of the different postcodes, along with, so the color essentially indicates the sample size, the dots indicate the train station. So, I mean, what is kind of obvious here, and I just kind of realized this after I did all the work and I was generating this plot, should have been obvious, but I'm not a local Sydney person, that, you know, some areas are quite large. And my view is that, you know, when you get to really, really large areas, there may be lots of kind of other confounding variables which I may not be controlling for, but I went with it anyway. The only thing I did, I cut this postcode kind of below the freeway. I just got rid of all the observations. So essentially, I just wanted to make that postcode a bit smaller. It was just so large that it's probably not right to assume that there's a common, sorry, there's one intercept for that area. So as you can see, I dropped all the Southeast Sydney areas, but yeah, all other areas are kept. And as you can see, there's lots of variation in the sample size for these different areas. Okay, so this is the results that I found. Personally, they weren't that exciting, but we'll see what we can get from it. So for all that work. So recall that this mu beta represents the mean of the common pi distribution on the train station variable. I find that the mean of this distribution is minus 0.006, and this is, you know, very, very close to the mean of the beta j's. So this indicates essentially for a 100% increase in the time it takes to walk to a train station, the value of rent declines by 0.06%. So if you want to think about that a bit more, it's just essentially saying if, you know, the property goes from being a 5-minute walk to a 25-minute walk on average, this reduces weekly rents by 2.4%. So that's the average impact across these different areas. So, sorry, I should have said this slide I just updated today. This was meant to be before that one. Apologies for that. So just quickly on the tools that I used to solve this problem. So this analysis was done using PyMC3, which is a probabilistic programming framework written in Python. And this is just a quote taken straight from their website. So PyMC3 is a new open source probabilistic programming framework with an intuitive and readable yet powerful syntax that is close to natural syntax statisticians use to describe a model. Now there's excellent blog posts and notebooks on hierarchical modeling using this tool if you're interested in. But you don't have to use PyMC3 in R. There's an excellent tool called Stan. I just chose PyMC3 because I was just trying to teach myself Python and thought I'll give it a go. So apologies, this slide was meant to be the before. I just quickly kind of came to my head that I should mention the tool that I used, and I did it before I came. So continuing on with the results, we see that it's kind of quite small. And this is kind of the distribution of this mu beta. And as we can see, there's kind of very little mass to the right of 0. So most of the areas essentially, you know, the value of rents go down as you move further and further away from a train station. But still, even with this distribution, it's you know, if you think about the credibility interval, you probably can't rule out that the true value is actually 0. Okay, so this is kind of the key part of why I wanted to use hierarchical modeling. It's just how it borrows statistical information from the other areas in order to inform the estimate of the area that you're interested in. So essentially, you're borrowing statistical strength, and what that does is reduce parameter uncertainty. And this is what we see here. So what I'm doing in this plot, I'm running a separate regression for each of the postcodes to determine the standard error of the parameter. I'm also getting the standard error of all the parameters for each postcode. And then I'm subtracting the standard error from the hierarchical model from the standard error from the separate model. And you can see what impact this has when you have small samples. Okay, so as you have small samples, there's lots of variability, and that leads to imprecision in your estimates. But using a hierarchical model, what we see is that imprecision declines. So, declines when you use a hierarchical model compared to a separate regression model. Obviously, as the sample sizes increase and become large enough, then you get an accurate enough estimate of that parameter, such that a hierarchical model matters less for getting precision. But when you're dealing with small samples, it can be extremely useful for increasing the precision in your estimates. And if you're doing any kind of analysis where you're trying to estimate the marginal impact on one variable or another, and you care about the precision of that estimate, and you have a small sample, and your data has a hierarchical structure, you should use this kind of framework. So this kind of plot, I'm not sure if it's going to convey the information that I want, but essentially what it just shows is that the hierarchical model shrinks these kind of large parameter estimates from the separate model, shrinks them towards the mean. So this kind of model can also act to shrink very large parameters, which is another benefit to using it. So so what we have here is a credibility interval for the different postcodes. So apologies if it's not readable, but essentially we have postcode 1 all the way up to postcode 100. So even though the marginal impact of living close to a train station is quite small, on average, what we see is that there's a fair bit of variation across the different postcodes. So, we have postcodes which, seems like there's kind of large value living next to a train station, whereas others we see that it actually, given these estimates, people pay more to live away from a train station. Okay, and this is just essentially a plot, just to see how it varies across the different regions. So what I have is in red, it's just essentially if this beta j is less than minus 0.01. So the reason why I chose minus 0.01 is because from that credibility interval plot before, for the areas which had a mean of minus 0.1 or less, the credibility interval didn't cross 0. So I just chose that as an arbitrary cutoff. So the green in turn represents all estimates where the mean is greater than minus 0.01. So what we see here is that there's a fair bit of variation across areas. But what we see, so I have a theory because I live in Marrickville and I kind of understand why Marrickville is green. But we see this kind of whole, I don't know if you guys call that inner west region of Sydney, is quite red. So in those regions, people do value living next to a train station. But in the other areas, it just kind of seems sporadic, and especially in the north here, people don't necessarily seem to value living next to a train station. So my hypothesis of why Marrickville's green is because in Marrickville, the train stations are kind of at the back of Marrickville, and Marrickville kind of reaches all the way up to Enmore. And, people value probably living close to Newtown, Enmore, more than living next to a train station. So for that reason, it's probably as you move further and further away from a train station, you're getting closer and closer to Enmore, and that's probably bringing the effect of living next to a train station down, or in fact pushing it up to be positive. Okay, so a key thing for people who do kind of economics or social scientists is, so we've estimated these parameters, and we've estimated these parameters by different locations. The question is whether we can make causal inferences. So is it actually living next to a train station that's essentially increasing the rent, or is it something else that we're not observing? So something, in order to make causal inferences, what we need is the correlation between the time it takes to walk to a station and the error of the regression to have zero correlation. So to be 0. Okay, so, and in my view, that may not be satisfied in this case. So for a whole range of areas, it could be that the train stations are in the middle of the postcode centre or the suburb centre, and it's living close to the suburb centre that people value as opposed to the train station. So all the amenities, restaurants and so on, maybe in the town centre, okay? And the train stations just happen to be in that location. And it's not the train stations that people value, but it's more essentially living close to these amenities. So while these hierarchical models have all these benefits, they don't necessarily allow you to get to causal inference, which is of interest to a lot of people. It also doesn't necessarily deal with omitted variable bias, but it does do a better job at dealing with that than these pool models. So the omitted variable bias will be partially dealt with by having postcode-specific mean intercepts, but it won't completely deal with it. So if you go to these areas, back to this plot, what you'll notice is that in some of these areas, especially down here, you have the train station, which is quite a distance away from the shore. Okay, so in those particular postcodes, it's possible that the further you live from a train station, the more valuable the property. And the reason why that is because you live closer to a shore and people value living next to a shore. So it's just kind of a couple of things to kind of keep in mind, that it doesn't, while it has lots of benefits in reducing imprecision, increasing predictive performance, it doesn't necessarily deal with problems of causal inference or omitted variable bias. But I plan to take this further and deal with those problems. So at the moment, I'm trying to work the distance walk to the nearest shoreline. And I'm also trying to determine kind of cluster of amenities for each postcode. So, and just the distance it takes to walk to them. And hopefully once I control for that, it will address the problems. Okay. So just to kind of conclude, so I found for a typical postcode, the value attached to living close to a station to be relatively low. But what we saw is that there's quite a bit of variation across the different postcodes. So although on average it's low, we do see quite a bit of variation. So in some areas it does seem like there is value attached to living close to a train station, even if one's not causing the other. And through the hierarchical model, I showed that it can be used to reduce parameter uncertainty and essentially shrink the parameters to more sensible values. Okay, so I'm not sure if I've gone over. Sorry, under in time, but that's it.
Fine. Is this the end of the presentation?
Sorry? Yeah.
Is this the end?
Yeah.
All right, well, I guess it's question time, folks, and we've got Jose here with the microphone.
You again?
Two more microphones there. So we've got time for a few questions.
Thanks for the talk, by the way.
Yeah.
I was just going to ask, given the results you got, would it have made sense to look and establish which ones were possible commuter towns, and then look at the value? Did you get a particular, because you showed that, see the high variation, showed that may have been masking the fact that some towns are specific commuter towns. If you just isolate those sort of, I guess, within a certain range commuter towns, what value did you get added to, or did you not look at that individually?
No, so I did not look at that individually, but I do understand what you're saying. So essentially my plan, I do have a strategy to address that problem. So with the census data, you can see essentially the postcodes which people live, and you can see the statistical areas which they travel to work to. So, and then so using that data for each postcode, we can kind of determine, the fraction of people which commute to work. Sorry, and it also includes the form of commuting. So while at present I don't have the information to determine what's a commuter area and what's not, I have considered that, and that is something that I'll plan to do, especially with the latest census, which is going to come out soon. So, but yeah, good point.
Thanks for the great presentation. I just about two things. So firstly, I thought you probably weren't using the fact that you have a Bayesian model quite seriously. So you had a non-trivial number of postcodes where the coefficient was positive and the confidence interval didn't include 0. And given the story you were starting off with, that is, and if you take a prior, if you construct a prior seriously from that story, that should not happen. There is no story in the way you are thinking about the model where it actually, you'd be happier living farther away from the train station, at least the way I was thinking about it. But maybe I'm wrong about that. The other thing I thought about was, because you were using a logarithmic transformation of the left-hand side variable, you are essentially assuming that the difference between living 1 minute away and 2 minutes away is the same as 5 minutes versus 10 minutes, which is the same as 10 minutes versus 20 minutes.
Yes, so,
right? So the point being that the 1 minute versus 2 minute, that, intuitively speaking, is not as much of a difference. It's kind of, you see the difference between half a minute versus 1 minute, that's not that much. But 5 minutes versus 10 minutes is intuitively quite a bit of a difference. So perhaps a more flexible functional form where you're estimating one more parameter, which kind of allows for a little bit more flexibility, like rather than kind of imposing logarithmic functional form could have been useful.
Yeah, no, so you're right. So, I mean, so it could just be that essentially there's no effect for the first 5 or 10 minutes. But so it's a log-log equation. So the impact of living 5 minutes to 10 minutes is going to be larger than living 20 minutes to 25 minutes. I mean, the log-log structure which I have in the equation, it's not going to have a linear marginal impact when you go, say, from 5 to 10 or 25 or 20 to 25. So, I mean, that should deal with that. But I agree with the point that you're saying that potentially for the first 10 minutes walk to a train station, there could be no impact. People associate, have no value whether it's 5 minutes or 10 minutes. I agree, that could be the case here because they're both relatively short walks and therefore you associate the same value. So for those initial values, I'd assume that, I should probably incorporate into the model. So potentially maybe a better way of doing it is having indicator variables where it's like 0 to 5, 5 to 10, or 0 to 10, 10 to 20, 20 to 30. Which is kind of, just kind of has a step function down. That may be a better way of modeling this. And that's something that I'll just look into to see if I can get better estimates.
Hi.
Yeah.
So how did you pick the prize that you used?
So which prize? The prize on the household specific?
Yeah.
So these ones?
Yeah, those ones.
So these ones just kind of came from just playing around with regressions on rental properties and just seeing how it varies when the number of bedrooms goes up by 1. How the price varies when the number of bathrooms goes up, whether you have a car park or not. So I've just been playing around with different models and just doing a whole bunch of things with this data, and these numbers just seem quite sensible what I've observed to date. And so you may feel that they're kind of tight price given the standard deviation, but again, just all the exercises that I've performed with different modeling just says that these are sensible numbers.
And is it possible to see the code and the data and things like that, play around with it? Because I have to pick houses sometimes.
So pick house. So
is it up on GitHub or anything like that?
So I have the code. I'm happy to put it up. So I'm happy to put it up. And then so I've got the code. I was playing with it just before this presentation. Still working on it. So I'm happy to kind of put it up and put it on the data on the data science page if people want to see. So that's no problem. Yeah.
Thanks for the very interesting talk. I was wondering, you said you're not interested in the predictions, but I was wondering, did you ever produce some predictions?
No, so I didn't. I didn't produce predictions. The short answer. So
I was wondering how you might be able to see how accurate the model was. It might give you another measure of how reliable your betas were.
Yeah, but so that could potentially be true, but it's just something that we know, like you could have a model that explains the variance well, but the parameter that you're interested in is not estimated well. So, I mean, that's just, like again, you could have, it's just the outcome in lots of research, so I didn't pursue that avenue. Sure, if the model predicts better, it could be the case that those betas are estimated better, but there's no guarantee of that.
Sure.
So I didn't bother with that exercise, but I agree that for this audience, potentially would have been of interest to provide predictions. Yeah.
How many months was the data collected over again?
So I was doing it essentially at the end of each month. I was going to each postcode and getting all the properties that were there from January to November.
So have you considered controlling for the increase in cost over time?
So I thought about that. Yeah. I thought about that, and so you're right. Like over time, the rental value increases, but this was my rationale for not including it, and I did do a model where I did include it, and it had no impact. There should be no relationship between the time which you collect the rental value and whether it's next to a train station. There should be no correlation between the months and whether you live next to a train station. So therefore, it's not going to impact the value of living next to a train station. Now, it could be the case that all the new properties are built right next to a train station. So over a longer period of time, it could potentially matter. But for the data which I'm looking at, there was no relationship between distance to the nearest train station and the time of the month. So again, if I was trying to predict the price, if that's what I was interested in, I should most certainly include month dummies. But because I'm not trying to predict, I'm just trying to measure the marginal impact, and there's no correlation between the marginal impact and the time, there was no need to include those dummies. It's not going to bias the result.
We've got time for 5 more questions. Who is next?
Hi, I'm Richard. Look, could you just go to the slide that showed the for each postcode the confidence intervals you had for the betas?
Sorry, yep.
That's it.
Yep.
Might be in my imagination. There seems to be a vast amount of autocorrelation in that. Are those postcodes sort of numbered sequentially?
So, no, so it's kind of, so you're saying the closer the postcode, the closer the geography.
Well,
is that your question?
What I'm wondering. I mean, you've just numbered the postcodes from 1 to 106 or whatever. If they're actually in numerical sequence, then I suppose you might expect them to be geographically close to each other, and therefore the autocorrelation makes some sort of sense. Is that how?
Yes. Yeah. So that's what is happening. Like there are areas which are next to each other, and yeah.
Thank you.
Hi. Thank you for the talk. Sorry. My question is, for the range of walking distances to a train station, what was roughly the range? Like, what was like the furthest house from a train station that was in the data?
Well, yeah, so it can go from 1 minute to an hour.
1 minute to an hour?
Yeah.
Could it be possibly that, let's say if it takes an hour to get to a train station, that you consider other forms of public transport, let's say a bus or potentially a ferry or other forms, so that the further it is, the less reliable or less possible it contributes to the model, considering there is alternative forms of public transport available?
Yeah. So I mean, we got to think about how. Yeah. So if you live further away, you'd consider an alternative mode of transport. But why would that necessarily affect the value of living next to a train station? So unless you're saying, well, you know, the further you're away, the more likely there is a bus stop, and you value a bus stop just as much as a train station.